Chapter 6, Applications of Trigonometry. Now this particular chapter kind of takes us back to the bare bones of right triangle trigonometry. We're going to see a few topics in this chapter, specifically vectors, parametric equations, polar equations, and complex numbers. And on the surface they may seem unrelated when in fact they are all directly related, and what connects them are the basic right triangle trigonometry formulas that are kind of going to be readdressed in each section just under a different name, a different packaging, but in the end it's really just the same set of formulas, the same set of processes in every single one of these sections. We start with lesson 6.1, vectors in the plane. Now if you have taken physics or currently taking physics, this lesson and really most of this chapter you're going to be very comfortable with. It's going to look very familiar, and it's pretty much the same stuff that you do in a physics class. If you have not taken physics and you're not currently in physics, no worries. It's all essentially just right triangle trigonometry. If you can handle basic right triangle trigonometry, then you can handle this. Now we start our discussion of vectors with the difference between speed and velocity. Now, when I say I'm going 25 miles per hour, my first question is always, is that a speed or is that a velocity? Because it's quite common in the non-math world to mix up these two words. They actually do not mean the same thing. A speed is when I'm going 25 miles per hour. A velocity is when I'm going 25 miles per hour in a particular direction. If I'm going 25 miles per hour north, I would call that a velocity, versus if I just say I'm going 25 miles per hour without indicating in which direction I'm going, that's referred to as a speed. In other words, a speed is just a magnitude. It's just a number. It just has a quantitative value that corresponds to it. Versus a velocity is a magnitude with direction. So both of these can be described as numbers, but velocity is special because that is a number that has direction. Now, because speed, if I say I'm going 25 miles per hour forward or 25 miles per hour backwards, the forwards and backwards don't really matter. So speed, just like distance, should always be positive, in that if I'm walking to McDonald's, no matter which direction I'm walking, I would always describe I'm walking 5 miles to McDonald's. And the same thing with speed. No matter which direction I'm going, I would always describe it as a positive 25 miles per hour. Versus velocity can be positive or negative. If I'm walking forward at 25 miles per hour, as soon as I say I'm walking forward at 25 miles per hour, I've defined forward to be positive because I used a positive number. Which means if I back up and start walking the other way 25 miles per hour, I'm going negative 25 miles per hour. The positive and the negative can indicate opposite directions. Now, what we do is we describe numbers like speed, numbers that have magnitude without direction. We call those scalar numbers. S-C-A-L-A-R, scalar numbers. Every number you've ever dealt with has been a scalar number up to this point. Once we take a number and throw in the concept of direction with that number, it's now called a vector. So a vector is a quantity with both magnitude and direction. If it only has magnitude, in other words, if I put the number 7 on a page, that number 7 is a scalar number because it has no direction. Versus if I take a number 7 and throw it across the room, well, now that 7 is traveling across the room, it has a vector, or it is a vector. Now, if I want to write a vector with scalar numbers, we represent them just by the Hindu Arabic 0 through 9 characters. With vectors, we represent it with a directed line segment. Not a ray, a directed line segment. This is a directed line segment. It is not a ray. In geometry, if I looked at this, I would think of this as a ray because it starts at P and it goes in the direction of Q, and the arrow would mean it goes on forever. When I'm talking about vectors, on the other hand, yes, it starts at P, we call that the initial point, but it doesn't go in the direction of Q forever, it stops at Q. Q is another point, we call it a terminal point. It goes from P and it ends at Q. The arrow doesn't indicate that it goes forever. The arrow means that it has direction. It's going from P towards Q. I could just as easily have put the arrow on the other end, and that would have meant it started at Q and headed towards P. Now, the notation we use for a vector is very similar to array. We can just use the two capital letters, P, Q, to represent P as the initial point, Q as the terminal point, and then put a little arrow over the top. That's perfectly fine to do that. Or we could also just use a single letter. Instead of using P and Q as your initial and terminal points, we could just pick any random letter we want. It's a vector. Why not just use V and call it vector V? Now, there's a couple different ways that we can notate it, though, other than just using the arrow. It's also quite common, especially in textbooks, to use just a bold V. Instead of using the arrow over the top, just use a bold letter, and that represents a vector as well. Now, speaking of that little arrow, just one more way that you can write a vector that unfortunately I was not able to do with my math type software that I use was the letter V, but instead of putting a full arrow over the top, you only have to put like a little half arrow over the top. It's quite common to use that notation instead of the full arrow. Just because, you know, mathematicians are lazy and we want to write things down quickly. It takes a while to, if I'm handwriting something, it takes a while to write things in bold, so typically we use that if it's in a textbook or typed. We'll write it like this. If it's handwritten, we'll often write it like that because it's just quicker. You can use the full arrow or the half arrow. The problem with the full arrow is that it's ambiguous. If I saw this right here, I might think that's array when in fact it's a vector. If I see that just half arrow right there, that's more indicative that it is a vector, not a array. So feel free to use any one of these notations as we go along. You'll see me jumping around and using all of them. Standard position of a vector is when the vector's initial point is on the origin. In other words, here is a coordinate plane, here is a vector, the initial point is on the origin, and it goes off in some random direction that's irrelevant. So if I have a vector somewhere else and I want to put it in standard position, it's just a matter of putting the initial point of that vector on the origin. Now you might notice that this kind of looks like an angle in standard position because it is an angle in standard position. It's going to be directly related to that as we go along. You'll realize that. Now, equivalent vectors is when we have two or more vectors with the same magnitude and direction. In other words, just like I can draw the number 7 all over the page, and they are all the same number 7, they are not different numbers because they're in different locations. They are the same number because they have the same quantity. I can draw multiple vectors on the screen. These are all the same vector. Just because they occupy different locations does not make them different vectors. As long as they are the same magnitude and the same direction, then they are the same vector. Only one of them is in standard position, the one with its origin at its initial point at the origin, but all of them are the same vectors. Component form of a vector. Now, it's important to distinguish between when something is a coordinate and when something is a vector. Notice here is the same dot on two sets of coordinate planes. On the left, I'm trying to describe a coordinate, so I will use an ordered pair, let's call it AB, to describe the value of that coordinate, the x value, the y value. And it's just a single point in space. A vector, on the other hand, is not a single point in space. It is the distance from the origin to that point. So instead of using the same notation that we use for a coordinate, parenthesis ordered pair, we still use an ordered pair, but we use arrow brackets. When there are arrow brackets, we're not talking about the vector. When there are arrow brackets, we're not talking about the coordinate. We are talking about the vector. So vector AB, arrow bracket AB, is the vector that begins at the origin and ends at the coordinate AB. Now, when I give you an initial point and a terminal point and I ask you what is the component form for a vector, we can use the handy-dandy head minus tail method to figure that out. So given initial coordinate x1, y1 and terminal coordinate x2, y2, so if I just give you two random coordinates, I tell you where it begins and where it ends, we can turn that into a component form simply by subtracting the x's and subtracting the y's. That's why we call it head minus tail. We take the head, which is the terminal point, and we take the tail, which is the initial point, and we just subtract. Just like if I wanted to know distance, if I'm starting at 7 and I'm ending at 14, I don't do 7 minus 14, I do 14 minus 7. The final position minus the initial position. The second x minus the first x. So here's an example. Vector PQ has initial point at 2, -5, and terminal point at -4, 6. First we want to find the component form, and then we want to draw a sketch in standard position. I'll give you a second to try it on your own, and then I'll walk you through how to do it. Alright, so we've got initial point at 2, -5, terminal point at -4, 6. So if I want vector PQ, remember it's head minus tail. I'm going to take the terminal point and subtract the initial point. Subtract the x's, subtract the y's. So we'll start with -4 take away 2, 6 take away -5, which gives us -6, 11 as our component form. Most common mistake is going to be those double negatives. Be very careful with those double negatives. So -6, 11 is my component form. I want to sketch it. So I can sketch it simply. It's perfectly fine to be lazy. You don't have to put all the tick marks on there. I'm just going to go ahead and put the tick marks I care about. As long as I label them, I'm good to go. So -6, 11, I want to draw a vector from the origin to the coordinate -6, 11. There is my sketch. Alright, which vectors are equivalent? So here are three vectors, vector RS, vector PQ, and vector AB. Each one describes the initial and the terminal point. Remember, when I say vector RS, that means it begins at R, it ends at S. So if I want to know which vectors are equivalent, all I need to do is figure out what their component forms are. So convert each of these to component form and figure out which ones are equivalent. Alright, so 2, 5 to 5, 3 should have given you 3, -2. PQ would be -3, 2, which means those are not equivalent. They are not the same number. They are actually the opposite of each other, so they are going in opposite directions. Their magnitude would be the same, but their directions would be opposite of each other, so those are not the same. Let's see what happens with AB. Is it going to match the first or the second? And it matches the first. So RS and AB are the same vector.